Hey everyone, welcome to the start of the video lectures for section 2.3 in the textbook. So section 2.3 talks about mathematical modeling. And so in this section we're going to go through what the book calls their three-step process for mathematical modeling, which also in my own opinion is a pretty good way to think about how models are built, constructed, and analyzed. So let's go ahead and jump on into that. So the book talks about a three-step process for mathematical modeling. Now, the first of these three steps comes from physics or biology, whatever science applies to whatever system you're trying to analyze, and it's where we actually build the model that we want to analyze. So step one is build the model. So like I said, this part comes from science. So this is where we use physical principles to write differential equations that will model our system. Now, in general, you're not going to be able to do the entire model exactly. It's going to be some sort of approximation. So if you're doing like motion of particles, well, things going really close to the speed of light don't really obey Newton's laws, but for most things that you look at in actual things you'll be considering, that's pretty close, and you can use Newton's law to sort of model motion. You're talking about chemistry, so chemical reactions evolve at certain rates. You can use that as an ODE that you want to set up. Again, it's probably not entirely exact, but it's close enough and it's a good approximation to get some decent results out of it. And so once you make those approximations, maybe even those assumptions as to how the process is going to behave, that takes care of building the model, and we have now written an ODE for our system. So the second step now is to analyze the ODE as you've written it. And this here is the math part. This is where you're taking the ODE stuff we're doing in class and using it to analyze whatever model you build. You want to figure out sort of what's going on with the model, how it behaves over short times, how it behaves over long times. All that is just being done using the math that we develop in this class and the ODE model that you wrote in step one. And even at this point, you may need to make even more assumptions. For instance, in the book, they talk about a pendulum, and you can use the linearized model for the pendulum, where instead of having a sine theta, you just have theta itself. That's a simplifying assumption that you might make at the mathematical modeling step, the mathematical step, step two, in order to make it easier for you to solve the equation. It's not necessarily physically accurate, but it is close from the mathematical point of view and might give you a reasonable assumption to start from so that you can try to solve first and then you work up to the more complicated one at the end. And finally, we get to step three, and step three is comparing with experimental results. Well, for building a model, it better model something. So the goal now is to see, okay, I've made this model, I've done the calculations, I see what my math says it should do. How well does that relate to what it actually does if I run the system? So this was basically, we just need to make sure the model works and that everything works out okay before we actually say, okay, this is a good model for this problem. Also in this part, we want to make sure that the solution that we do get from the analyze the model from the mathematical perspective makes physical sense. For instance, if you want to model population and your population goes negative, well, something's not right there because population shouldn't be negative. If you're trying to say compute some sort of area or some sort of volume calculation and you get a negative number, also a bad thing. Negative numbers in general aren't good when you're trying to count stuff. So you're looking for any inconsistencies there with what you're trying to calculate and what you end up getting. And any of those would be a good indication that your model is not very good, or at least that you need to refine it a little bit to make it better before it becomes a good model for this problem. And after all that's said and done, if you get the result that it's not consistent or it's not a good thing, you get models that don't, you get things that don't work out well or that the solution becomes unreasonable very quickly, that's just an indication that you might need to look for another model. So if it doesn't work, maybe you have to find a different equation to set up your system and sort of work through it a different way to get an actual good model for it. So this means you might need a new model. All right, so there is the three-step process for developing a mathematical model as described by the book. Build the model from physical principles, analyze the model using math, and then compare with experiments to make sure that what you got is actually physically reasonable. So we'll get some more practice doing things like this over the next couple of videos and in class on Monday. So that's it for this video. Thanks a lot for watching, and I will see you in the next one.